All right, so in this video, we're going to be talking a little bit about the equation of a plane in 3 dimensions. Now, in 3 dimensions, the equation of a plane, which is a 2-dimensional object, is going to be a linear equation. Typically, when you have a linear equation, represents a space that is 1 dimension less than the space that it's in. So when you have a linear equation in 2 dimensions, you have a 1-dimensional line. But in 3 dimensions, you get a 2-dimensional plane. So the general form of the equation that we're going to be working with depends on a vector and a set of points, or a single point. The vector is going to be the vector that is perpendicular to the plane, and the point is going to be a point that is in the plane. Now, one important aspect of this equation of the plane is that the ABC vector is the vector that is normal to the plane. So you often hear that term. It's the vector perpendicular to the plane, but it's often referred to as the normal vector. That's another term for perpendicular in this context. And then, of course, a point on the plane, x naught, y naught, z naught. Now, one other important thing to keep in mind is that this is an equation. One of the errors that some of my students will frequently make, in which I've developed something of a pet peeve about, is to put the vector and points together and stop right here before the equation and not write the equals 0. And I suppose there's a sense in which that's the most important part, but it's not an equation if it doesn't have the equals 0. So you need the whole thing when you're putting this together. Now, for simple problems, you just need these 2 things. Now, in another video, I'm going to go through the different ways that you might be given information that you would have to develop in order to get to the equation of a plane in 3 dimensions. But for this video, we're just going to look at a very simple example and put the equation together. So let's say I have a normal vector to the plane is specifically 3, -2, 4, and a point on the plane is 5, 1, -6. So then our equation of the plane is going to be 3x - 5 plus 1 y plus 2 minus 6 z, oh, sorry, plus 4. I'm looking at the wrong thing. Yeah, I'm looking at the wrong thing. There we go. The coefficients come from the vector normal to the plane, 3, -2, 4, and then the point comes from the point, -5, -1, and then z plus 6. And then, of course, you could simplify. Now, typically, I don't require my own students to do the simplification. Because it's just an opportunity to make additional mistakes. Let's see, -15 plus 2 plus 24, I'm going to get plus 11 equals 0. Now, any equation of a plane that is parallel to this plane will have will be reducible to this set of coefficients. So you could have multiples of these coefficients. Again, you can have vectors which are the same, pointing in the same direction, which are different lengths. But assuming that you reduce all of the coefficients to match these, then the only difference would be this constant. This constant changes the point in the space that the plane passes through. And so if you change that constant, it's still oriented in the same way, but now it's passing through a different set of points. Now, one other thing that I want to do before we go on from this video is I want to also talk about sketching a plane in 3 dimensions. Now, typically, it's very difficult. I should say it's more difficult to sketch a plane that doesn't intersect in the first octant. But if you do have a plane that intersects in the first octant, which is going to happen a lot when we're doing multivariable calculus, because we want to be able to set up our integrals and things like that. So most of the time, we're going to be looking at planes that are actually just in the first octant, or that cut through the first octant in some way. And so typically, what you're going to have for that kind of a plane is you're going to have something where all of the constants are in your equation, all of the coefficients of your x, y, and z are positive, and the constant, the constant at the end of your equation, if you move this constant to the other side, is also going to be positive. That's going to guarantee that all of your x, y, and z intercepts are positive and therefore intersect with the xy plane. So if we want to draw this, I'm going to insert a drawing canvas, and then I am going to draw a 3D grid here. I'm not going to do the whole grid, just the axes. And then we'll draw on it. Now, recall that this, in the standard right-hand coordinate system, typically this is x, this is y, and this is z. Now, if I'm plotting this point up here, if I want the x-intercept, I'm going to let y and z become 0, and then I'm going to solve the remaining equation. So if all I have left, if this is 0 and this is 0, and all I have left is 2x is equal to 10, then my x-intercept is going to be 5. So 1, 2, 3, 4, 5. My point is going to be there. If I want the y-intercept, I'm going to let x and z be 0. And then all I'm going to have left is 5y is equal to 10, which is going to give me 1, 2. So that point is going to be there. And then if I want the z-intercept, I'm going to let x and y be 0, and I'm going to have z equals 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That'll be my 10. And then I'm going to put straight lines in here. So between my z-intercept and my x-intercept, let's change the color. Between my z-intercept and my y-intercept, and then between my x-intercept and my y-intercept. And so now this, again, the plane extends beyond these axes, but this is the portion of the plane that intersects in the first octant. And so you'll often again, later on in the course, you'll often have problems where you have a tetrahedron or something like that, which is bounded by a given plane. In the first octave, the coordinates are the other four sides. And so then you'll be finding the volume of that tetrahedron. So again, this is typical for these kinds of sketching problems. Now, you can still do this sketch if the intercepts are in different quadrants. We would extend our axes to positive and negative directions. We would plot the points exactly the same way, and then we would connect the dots exactly the same way. It's a little harder to visualize when it's not that side that's coming out of the page at us. But nonetheless, the steps and the procedures are exactly the same.